So just a reminder, what we were working with when we were doing the antiderivative of these using the technique of u substitution, we were always ending up with something with a plus c. This is what's called an indefinite integral. Indefinite because c is not defined. Now when we want to have bounds, we call that a definite integral. And we put brackets on that, and we end up with capital F of b plus c minus capital F of a plus c. This is the fundamental theorem of calculus, part 1, and this is called a definite integral. Now when you're doing this along with u substitution, you're going to have to adjust your bounds, because since you are changing to a whole new variable, the original bounds are based on the variable of x. When you choose to switch and substitute into a u variable, you have to convert your bounds as well so that they are now in terms of u. So let me show you how to do that. So here's an example of a product. We talked about that yesterday. So tangent of x times the secant squared of x dx. Now first I want to make sure that we've chosen our u correctly for this. Okay, any suggestions from you guys? What do you think we should choose for u? Go ahead. Okay, so Luke is thinking, this looks to him, at least I think you're thinking this, that maybe this is looking like secant of x quantity squared and then having a dx like that. Okay, so he's thinking that secant x is the one that's in the parentheses, and then that would be a choice for u that he could use. Okay, so that's one thinking. We could try that out. Anything else? Any other suggestions? Think ahead down the process of what should happen in u substitution. Abby? Oh, say that again? You want to use the whole secant squared of x. Okay, because? Okay, okay. So you're seeing the connection between tangent and secant squared. Okay, Andrew, were you going to say the same thing? U as tangent x. Okay, why? Okay. All right, so both of you are seeing that there is a connection between tangent and secant squared. One is the derivative of the other. One is the antiderivative of the other. So which one do you want to choose? Okay. As you're choosing your u, you want to choose the one that is like the original one that not, you're talking about antiderivative, but you would want to choose tangent here. I think that, Luke, your method would actually work in the long run, but you would have to do 2 u substitutions in yours. Like you would substitute and clean it up and then realize that you had to make another u substitution and do it again, which we would call that a uv substitution, because first you choose u and then you can't use u again and you have to choose a different letter. You could choose whatever letter you wanted, but I think the same thing is going to happen with yours if you go that way. Okay, the best choice here would be for u. So let's look at why that is. If we choose u to be tangent x, knowing our derivatives, that this is going to be secant squared x, automatically, if you can like fast forward through some of those steps in your mind, if you can see that, oh, as I rearrange that, dx by itself is going to be du over secant squared, which means it would reduce away the secant squared I already had. I just want to think through, so like Luke, if we chose u to be secant x, du dx is secant tangent, and then if we rearrange that, we would end up with du over secant x tangent x equals dx, which would partially reduce, but not fully reduce, everything that we would need, which would be okay. It would, but we would maybe have to do it again. All right, so I think we're going to stick with u being, we'll go with this one as our option. Okay, now, let's also consider that this has bounds. So go back to your example and add 0 and add pi fourths as your bounds. When you do a u substitution on a problem with bounds, you have to take each bound and convert it to its corresponding value in the u substitution. In other words, you need to take 0 and plug it in for x in your u substitution and see what you get. You also need to take pi fourths and plug it in to the value of tan x and see what you get. So let's kind of track that. Taking 0, I'm putting it into tangent of 0. Tangent of 0 is 0, so the lower bound stays 0. I did not convert. We're going to take pi fourths as the upper bound. We're going to plug that into what we chose for u. So it would be tangent of pi fourths. And the tangent of pi fourths is 1. So my upper bound is now 1. And so I'm going to do my u substitution and my bound conversion. And I'll have a cleaner, simpler integral to solve. All right, so let's go back. I'm changing colors to show I'm going back. Okay, I chose tan to be u. Secant squared I'm keeping. Dx is du over secant squared. And my bounds are 0 to 1 instead of 0 to pi fourths. So what I see happen is the reducing, and there's no constants to pull out, and I'm left with 0 to 1 of u du, which is about as simple an integral as you could get. So then I do my antiderivative, 1/2 u squared plus c, and you never have to go back. You never have to change x, the u, back into tangent because you've converted your bounds too. And so I can just, from this point on, just go with the new bounds that I have. So this would be 1/2 times 1 squared plus c minus 1/2 times 0 squared plus c. So overall the answer is half. I actually prefer doing problems with bounds because I never have to go back and resubstitute. I just stick with my simpler bounds. 0 and 1 are pretty simple in terms of bounds. So I'm going to do another one of those with you. All right, so let's look at the definite integral from 0 to half of 1 over the quantity 2x plus 1 cubed dx. So first you would identify your u choice. Maybe you would want to rewrite this as as 2x plus 1 to the negative third dx, just to help you see, okay, yep, I know what my u is going to be. And so I'm going to set up my u would be the choice of 2x plus 1. My derivative on that is the constant 2, which converts into du over 2 being equal to dx. I also want to take my two bounds and plug them into what I chose for u. So 0 will get plugged into 2 times 0 plus 1, because that was what I chose for u, 2x plus 1. 0 is an x value. So 1 is my new lower bound. 1/2 gets plugged into 2 times 1/2 plus 1. That turns out to be 2. And so my upper bound is now 2. All right, so now I'm going to say equals to show that I'm continuing my original problem. So my bounds are now 1 to 2. My parentheses now have a u on the inside. And my dx is replaced with du over 2, which means I can pull the constant of 1/2 out of my integral. And then you're ready to do the antiderivative using the fundamental theorem of calculus. So 1/2 times the bracket, my u is now u to the negative 2 plus c, but I also need to divide by the new power, so that would be negative 1/2. And my bounds are 1 to 2. And remember, I never have to go back to the original value of the bounds. I don't have to go back to the original value of u either. I can just go from here. So I have, when I combine my coefficients, negative 1/4 times 2 to the negative 2 plus c minus negative 1/4 times 1 to the negative 2 plus c. So we just want to clean all of that up. That's negative 1/4 times positive 1/4. The plus c's cancel out. And then plus 1/4. So we're looking at negative 1/16 plus 1/4 if you add fractions, negative 1/16 plus 4/16, so altogether 3/16. This all still represents area. This is the net area, or the net displacement, of the original integral 1 over the quantity 2x plus 1 cubed on the original bound 0 to 1. And so the value of 3/16 represents the net area in that. Just like the original one we did before, the net area underneath the complex equation tan times secant squared from 0 to pi fourths works out to be half. That's what the integral represents. Okay, do you want to see another one, or do you feel like that was enough? I feel like it was enough, but if you have another one, I can do another one with you. Okay, so that gives you, like, yeah, say it again. A tricky one. All right, how about x squared multiplied by the square root of 5 plus 2x cubed dx? And we go on bounds from 1 to 3. Luke, you want to practice picking u? Yeah, I think that's good. All right, u is 5 plus 2x to the third, which means the derivative on that would be 6x squared. And then if we rearrange our terms, we have du over 6x squared is equal to dx. Let's also convert the bounds. So 1 would get plugged into 5 plus 2 times 1 cubed. So what is that going to give you, Luke? Okay. And then 3 would get plugged into 5 plus 2 times 3 cubed. And so what bound would that give you? Yeah. Okay. All right. So our integral now becomes 7 to 59, which you might not think, oh, okay, but it's okay. And we have x squared. And then you chose the square root to be u. And then we've got du over 6x squared. So when we simplify, the x squared terms pull out, and 1/6 is the coefficient out front, from 7 to 59. And I'm going to write this as u to the half du, because for me, my brain just likes to see the half. All right, the antiderivative u to the half is u to the 3/2 times the 2/3 plus the constant c, and we're going from 7 to 59. When we simplify that, we get 1/9. And then I'm looking at the square root of u cubed plus c, going from 7 to 59. So then when we substitute in, you can leave it as 1/9 of the square root of 59 cubed minus 1/9 of the square root of 7 cubed. Okay, you don't necessarily have to expand that to get anything. You can just leave it like that. If you wanted to factor the 1/9 out, I suppose you could. Okay, you could have 1/9 times the quantity, the square root of 59 cubed, minus the square root of 7 cubed. That would maybe be one thing you could do, or put the whole thing over 9 or something. But you don't have to get a decimal value or these really big square roots. You can leave it.